Welcome to the first lecture on functional analysis. Before we go to the motivation and introduction, we would like to answer briefly what is functional analysis. In his book, Dudon, History on Functional Analysis, it can be defined as the study of topological vector spaces and the properties of continuous maps between such spaces. And so here we have two keywords, topological and vector spaces. So functional analysis uses the main ideas of topology, that is the concept of open sets, and hence the concept of convergence, continuity, compactness, among others. And it also utilizes the ideas in algebra, where in a vector space, say, you have the concept of addition and scalar vector multiplication. These topological vector spaces, uh, in most cases are called function spaces because these spaces contain functions. Well, roughly, one can also say that functional analysis is an infinite dimensional linear algebra. But of course, there is more to functional analysis than this rough analogy. So as a motivation, functional analysis can be used as a tool in studying or analyzing static and dynamic evolution equations. So for instance, it can be used in the study of delay differential equations. So unlike in ordinary differential equations, where the state depends only on the initial time, in delay differential equations, the future trajectory depends on what we call a history. And this history is a function, let's say, of time. And this presence of history or delay can have a destabilizing effect on the trajectory of the solution. The second example is stochastic differential equations, where instead of having a smooth curve or trajectory that solves the differential equation, you have some sort of randomness. And finally, we also have the so-called partial differential equations, wherein your independent variables can be more than one. In this case, let's say in the x and in the y direction. And in that case, the graph would be a surface. And in this scenario, the solution would be a function of two variables. So these differential equations are called infinite dimensional differential equations. This comes from the fact that the state space, which roughly is a space of functions, it cannot be generated by a finite basis. By basis here, we mean in the sense of linear algebra. Okay. Well, you can think of, for example, the vector space of polynomials having real coefficients. That vector space is not a finite dimensional because you cannot find a finite spanning set for the set of all polynomials having real coefficients. Because if you have a finite list or a finite basis, you can take the largest degree. And then if you take a polynomial having a degree larger than the largest degree of the finite basis, then obviously you cannot span or you cannot write that polynomial in terms of that finite basis. So with regards to this so-called infinite dimensional differential equations, we would like to ask a fundamental question. So the existence and uniqueness of solutions. But of course, in terms of these differential equations, we need to define, or we need to specify, what do you mean by a solution. So one approach, and this is the case of partial differential equations, one would consider the so-called finite dimensional approximations. And in these cases, we have ordinary differential equations. And with this sequence of approximations, we want to show that the approximations indeed converge to a solution that we define. And in this case, this is the well-known Fado-Galerkin method. Okay. And in the context of differential equations or partial differential equations, notion of solutions may vary. And in the literature, there are what we call strong solutions, weak solutions, and even what we call very weak solutions. So roughly speaking, weak or very weak solutions does not satisfy the differential equations in the usual sense, but in some generalized sense. And we will discuss this in future lectures. So knowing that we have a concept of solution and it exists, the next natural question would be, is it unique? Well, in most cases, it can be shown that the solution is unique, but there are still open problems in the field of partial differential equations where uniqueness of solutions are not guaranteed. For instance, you have either the, let's say, the incompressible or compressible Euler, and for instance, also the Navier-Stokes equations in fluid dynamics. So if there are many solutions, can we impose conditions that will guarantee uniqueness? So in the field of fluid dynamics, for instance, there is what we call entropy conditions that allows to pick the physically relevant solution. Okay, so that's one issue. Do we know that the infinite dimensional differential equations have a unique solution? The next aspect is numerical approximation. And in, let's say, in the area of what you call the finite element method or finite element analysis, this leads to solving a large but sparse linear system. Okay. Large here means that the size of the matrix is huge. For instance, it can take a million degrees of freedom. By sparse here, we mean that there are a lot of zero entries in the system matrix. So for instance, the density or the number of non-zero entries can be linear in comparison to the size of the matrix, which is quadratic. And of course, solving this sparse linear system, so increasing the degree, okay, or increasing the size of this, we hope to have a better approximation of the differential equations. And again, the natural question is, do the approximations converge to a solution? And if they were, how fast? What is the convergence rate? Of course, in the implementation, these issues are important because, let's say you want to implement your algorithm in a computer, and if you have an idea of, let's say, the time and memory complexity of your algorithm, as long as, and also uh, uh, the convergence rate, then we could choose what method to apply in the implementation. So one of our goals is the following. We want to develop notions of convergence of a sequence of functions and study their properties. So the keyword here is convergence. So if you notice, both in the existence and uniqueness of solutions, as well as in the numerical approximations, we have the issue of convergence. So how do we say that a sequence of functions converge to another function? Okay. And we would discuss several notions of convergence later. What is the minimal requirement for convergence? Okay, so for convergence per sequence, it suffices to have the notion of open sets. Or in this case, if you have a topology on your vector space. So convergence is basically the following. So I have a sequence x sub n from 1 to infinity. Then this sequence converges to x, which we call the limit, if, okay, I take any open set, this case, as an illustration, the shaded region. If I have an open set containing the limit x, then all except for a finite terms of the sequence will be in that open set. So in this case, on or after the index n, all of the terms of the sequence lies in the open set. So that is the definition of a convergence with respect to a topology. Okay, so it is enough to have the notion of open sets, and probably you might know open sets can be generated via a metric. Okay, so if you have the concept of a metric or a distance, you can define the concept of open balls, and these open balls serves as the fundamental building blocks of the open sets. Okay. Well, roughly speaking, in terms of the above illustration, so we can say that a sequence converges to a limit x if uh, for all terms of the sequence except for a finite, which has not been displayed here, except for a finite number, if you take the distances between the terms of the sequence, these distances should be small. Let's say less than some prescribed uh, number epsilon. Okay, and you can take this epsilon small enough. So in that way, the distances of the terms of the sequence, except for a finite number, is very small. And intuitively, those terms should be close to the limit. Well, you can think of length as the distance relative to a given point. Okay. And this given point is typically or usually the zero element of your vector space. This length generalizes, for instance, in R, your absolute value, or in general in Rn, the Euclidean space Rn, your Euclidean norm. Okay. So norms generalizes the concept of lengths in the case of the set of real numbers. Well, to see this, so suppose I have two vectors, x and x sub n. Okay, so the distance between x and x sub n, after some translation, meaning by subtracting x both sides here, okay, after some translation, is the same as the length of the vector consisting of the difference of xn and x. So if you translate this line here, wherein one point is located on the origin, let's say, then the length must not change. Okay. So here you can think of 0 as your reference point or reference vector. Okay, so the distance between two vectors by translation can be thought as a length of the difference of the vectors, and vice versa. If you translate this back, the length of the vector is the distance between the two vectors. So therefore, a length can give the notion of a distance. We could also generate the concept of a length if you have the concept of angles or inner product. Okay. So for instance, in the Euclidean space, the inner product, let's say, of two vectors x and y is nothing but the sum of the products of the corresponding components, say x sub I and y sub I. Okay. And if you take y to be x, you end up with the following formula. So if y is equal to x, okay, and this is, as you might know, the square of the Euclidean norm. Okay. So the inner product of a vector with itself is nothing but the square of the Euclidean norm. Okay. So if you have the concept of an inner product, then you have a concept of length or a norm just by simply taking the square root of the inner product of the vector with itself. So notion of inner products leads to the concept of lengths. On the other way around, inner products also lead to the concept of angles. So in calculus, let's say you have a vector x and a vector y, you could calculate the angle between these two vectors, okay, just by taking the, let's say here, the cosine inverse of the inner product of the two vectors divided by the product of the norms. Of course, provided that neither of the vectors are 0. Okay, so you see here, you have the inner product. So the concept of angles is, let's say, very useful in the field of optimization, let's say, or approximation. So to state the problem, suppose we want to solve a certain problem, and the solution to that problem, or the desired ideal solution to that problem, is outside what we call a feasible search region. Okay. Well, in certain cases, let's say due to the limited amount of resources, you cannot take all points in your solution space you cannot take any point in your solution space, and you are only restricted to search in what we call a feasible region. And in the situation where the ideal solution or ideal point lies outside the feasible search direction, then what we do is we want to determine the point in the feasible region that is very close, or which is closest to the ideal point. And in this case, one can find that via projection, meaning you take the tangent to that point, assuming that, of course, the tangent exists. Then take the vector from the point on the search region to the ideal point that is orthogonal to the tangent vector. And that is the idea of projection. Okay. So take note here that we need the concept of an angle. In this case, the projection has a 90-degree angle with respect to the tangent to the curve at the closest point. So that is orthogonality, or in 2 dimensions, perpendicularity. So going back to the previous slides. So here again, the convergence of a sequence. For convergence of sequences, it is enough to have the notion of open sets. Open sets can be generated by a metric. A metric can be derived from the concept of a norm, which is the generalization of the length. And finally, if you have an inner product with your set, then you can define a length or a norm. And in this course, we will discuss those concepts. So we have different underlying spaces with these objects. So for open sets, you have the topological spaces. For the concept of distance, you have the metric spaces. The concept of length, you have the norm spaces. And finally, if you have the concept of angles, then this would be the inner product spaces. So here, the largest is the topological spaces, and the smallest among the collections are the inner product spaces. Because, as we know, angles lead to lengths, lengths lead to distances, and distances leads to open sets. Okay. So in the next lecture, we will discuss topological spaces and metric spaces in a brief fashion. Most of our lecture in this course will deal with these 2 spaces, the norm spaces and the inner product spaces. Okay, so that's it for an additional overview on functional analysis. I encourage you to read the lecture notes. So that's it for the motivation and introduction. For the next lecture, we will discuss topological spaces.